We're going to take a look at a physical property that you're probably aware of, but it's our first quantitative one, and that's density. And this little graphic here is something I want you to be able to explain to me at the end of the section on density, why I chose this. So you're going to be able to explain the difference between mass and density, both with numbers and in plain English, and some of its implications. In metric, there are only a few fundamental units, just 7 of them, for distance, mass, time, temperature, electric current, light intensity, and amount of substance. We call metric MKS for meters, kilograms, and seconds. Temperature is in Kelvin, not in Celsius. They're equivalent to each other, and we've already done amperes. So it's only candela and moles left to go. Everything else is assembled from these. There are hundreds of units, but they all come from these 7. So for example, speed is distance over time. Area is distance times distance. So you construct these. Amperes, you learn itself is actually a constructed unit, but it's considered to be fundamental for really complicated reasons. So we have area, volume, speed. Energy in joules is actually a kilogram meter squared per second squared, which is why we gave it the nickname joule. And all the electrical terms we've used are actually combinations of the other ones. And so the triple equal sign is what we use to show that things are identically the same. So 1 joule is identical to a kilogram meter squared per second squared. The derived units become really important later in chemistry and physics. Our first derived unit is fluffiness, density. It's a measure of how compact or fluffy something is. And I would like you to use the term fluffy and squishy, right? So you convince me you know which way you're talking about. So density is equal to mass divided by volume. Something that is fluffy does not have a lot of particles in the same amount of size. Okay, so this is fluffy, this is just right, and that's too squishy. The formula is meaningless if you don't understand it. So this formula has meaning. The mass is basically a count of the atoms in a way. It's telling you how much matter there is. And that amount of matter has nothing to do with gravity. I'll give you an example. If you had 2 golf ball sized objects, one of them was literally a ping pong ball, and the other one was solid lead, and they were both painted white. Do you actually think if you went on the space station and someone whipped the lead ball at your head, that it would not hurt because there's no gravity? Would you expect it just to bounce off going, wow, it's weightless now? No, the matter is still there. The atoms are there. So we take the total amount of atomic particles, the mass, and we divide it by the space they occupy, the volume, and then we get a measure of squishiness or fluffiness called a gram per cubic centimeter. And I want you to think of it as gram for every cubic centimeter. And a cubic centimeter is about the size of a sugar cube. So how much would a sugar cube sized piece weigh? So we do not measure density with a densityometer. We calculate it from 2 other units using this formula. We standardize it to 1 cubic centimeter, sometimes a cubic meter, sometimes a cubic kilometer. But basically, if I gave you an object, we're just cutting off one little tiny cube of it and getting that mass of a sugar cube sized piece. Grams for every cubic centimeter. Now, most of you know how to do basic volumes. You probably can do at least 2 of these. You might be able to do all 5 at this point. Which ones do I want you to be able to use? Just the cubic shapes. If you want to do cylinders and spheres, that's advanced work, right? And volumes can also be used with measuring cups, and this is very convenient for liquids. In metric, a milliliter is the liquid measure and the cubic centimeter is the solid one. Fortunately, they're the same thing. So 1 milliliter and 1 cubic centimeter